recording. Section 6.3 and 6.4 are tomorrow. On Saturday is section 6.5 and the R4 review to date, which is loaded into module 4. And then you have your quiz 7. We only have 2 more quizzes, quiz 7 and quiz 8, and then you're done with the quizzes. Today we're going to do section 6.4 on the logarithmic function, and the best way to do this is to actually springboard or use yesterday's lecture to start it. So yesterday we graphed, so we'll do a brief review, and we did f of x equals 2 to the x. And what we did then was we built a table of values, and we did -2, -1, 0, 1, and 2. And we got 1/4, 1/2, 1, 2, and 4. And so that picture from yesterday looked something like this. And again, this is in your notes. So, so -2, we're at 1/4, -1, we're at 1/2, 2, and 4. So this is 2 to the x. And we talked about its different properties yesterday, and we talked about the fact that it's an increasing function, it has a y-intercept, it does have a asymptote that's sitting on top of the x-axis, so it has a horizontal asymptote. It can never go negative. And the other thing we did talk about briefly, but has to get tied in today, is the fact that whatever this base is on the exponent, that base has to be greater than 0, and the base itself cannot equal 0, or can't equal 1, sorry, because that wouldn't be a very exciting function. Okay, we did comment that this was a one-to-one function, which does mean that it has an inverse. So today we're going to take a look at the inverse. So because it's one-to-one, it has an inverse. Okay, so we're going to go about this a couple of ways. One way, we're going to go graph it. So let's graph that inverse function. Let's graph. So to do that, all we have to do is take our x and y's and then just flip them. Well, that's easy enough to do. So over here, I'm going to come in and take my values and essentially just trade out the x's and the y's. So it becomes 1/4, that's a positive, not a negative. 1/4, comma, -2. We'd have 1/2 at -1. We'd have 1, 0. We'd have 2, 1. And then we would have 4, 2. So I simply switched the columns that were x and y. So what I want to do is I want to come in and plot those points. So at 1/4, we're down at -2. So it's really close to the y-axis at 1/4, -2. At 1/2, we're down at -1. We have a point at 1, 0. We have a point at 2, 1. Sorry. That's the dogs barking at the tree, guys. And then we have a point at 4, comma 2, which would be up here. So the graph of the inverse looks like this. And there's our inverse function. Well, wait a minute. What are we going to call the inverse function? So if the original function was y equals 2x, y equals 2 to the x, then the inverse function, all we're doing is switching the x's and the y's. So this would be x equals 2 to the y power. And notice that works. So if we come in here and pick our y values, then 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1, and so forth. So that definitely works in terms of our inverse functions ideas. This original function had a horizontal asymptote, so the inverse function has a vertical asymptote at x equals 0. Cool. So for that inverse function and the original function, so what we're going to do is make a little chart about information. So just so that we have what's going on. The original function was y equals 2 to the x. So the inverse function is x equals 2 to the y. So on the original function, we know its domain was all real numbers from yesterday, and the range was 0 to infinity. So for our inverse function, we're just going to flip that information. So its domain is 0 to infinity, and its range is negative infinity to infinity, which fits our picture. So we can see from left to right, we're starting at 0 and going off to the right. And in terms of bottom to top, we're going from negative infinity to infinity. That definitely works. On the original function, we had a y-intercept at 0, 1. And when we flip that, we'll get an x-intercept of 1, 0. So again, everything that's x's and y's is just getting switched. The other thing to note is this had a horizontal asymptote at y equal to 0. The inverse has a vertical asymptote at x equals 0. Okay. So we can graph the inverse. We know information about the inverse. What's weird about the inverse is we are just not trained to think of this in terms of x equal. We are trained to think of this as y equal. And how am I going to write this as a function, right? So what we're going to do instead is create a new function that lets us translate that x equals 2 to the y. So that's all the background. Now we come in and actually come in and define a logarithmic function. So this inverse function that we're talking about here is really a logarithmic function. And again, that should not be a surprise because you guys all saw that in your 101 class. So that's our lead in. Okay, so then we're going to come in and define the logarithmic function. So the logarithmic function, which we will abbreviate as a log function just to make the spelling easier on everybody. So the logarithmic function to the base a. So we'll go for that generic base again. So not a base 2, but a base a. Where a is, same restrictions, greater than 0, not equal to 1, is denoted by, okay. So we're going to write that as y equals log base a of x. Now I know you've all seen this before, but just as a reminder, when you write this on your lined notebook paper, that the y, the log, and the x are all written as normal size font, and then the little a down here is a subscript. So that's really messy. Let me write that bigger. So we have y equals log base a of x. And notice how I said that. I said log base a of x. So what that means, so that is if and only if a to the y is equal to x, which ties into the graph we just had, because we just had 2 to the y is equal to x. This then lets us write it as a function. So back over here, we can add our function notation of f of x equals. So now we're back into world or area that's comfortable in terms of how we write things. So f of x, which is really the y, is log base a of x. And that is true if and only if a to the y is equal to x. So this flips the x and the y from yesterday's lecture into the correct for the inverse function. Okay, so generally what you start with when you do the logarithmic function is just how to go back and forth between the different forms. So this is basically like saying hello in 2 different languages. So here it is in English and here it is in Greek kind of thing. So what we're going to do is build a table. So we're going to convert between log form and exponential form. Like Matt and Adam have already seen this out of me. So, okay, so let's put the the log form in this column. And then next to it, we're going to do the exponential form. So we'll write the definition back up. So we said that if log base A of x was equal to y, that meant that a to the y is equal to x. So this is what I call is the lassoing theory. In other words, when you start to go back and forth, you start off by using the base, always the base. You then go across the equal sign and pick up the exponent, and then set it equal to the inside thing. Okay. So, in other words, if we have log base A of m is equal to t, and I'm just making them up, they're meaningless at this point. So log base A of m equals t, that means that a to the t power is equal to m. So again, I started with the base, I went across the equal sign to pick up the t, then I come back in and pick up the inside of that logarithm. We could also have log base e of 5 is equal to r. So log base e of 5 is equal to r. So when I rewrite that, I pick up the base, which is e. I raise it across the equal sign to the r. That's where the exponent comes from. Set it equal to the inside, which is 5. We could also have log base 10 of 100 is equal to 2. This one should make sense when we rewrite it. So what we're going to have is 10 to the second power is equal to 100, which is true. 10 squared equals 100. So. Okay, so that's how to go from log form to exponential form. Any questions about that? All good?
No, I'm good.
Yay. Okay, now I'm going to erase and go the other way. So now we're going to start over in the right side and try to get to the left side. So let's start off with one that we do know. So we know that what, 5 to the third power is equal to 125. So 5 cubed is 125. So when I switch it to the log form, I'm going to do the same thing. I'm going to write the word log. I'm going to pick up the base, which is the 5. I go across the equal sign. So again, I lasso the base. I go across the equal sign. I'll pick up the 125 and set it equal to the exponent, which is 3. So log base 5 of 125 is equal to 3. That's the same statement as 5 cubed equals 125. So what if we have e to the 6 is equal to m? So e to the 6 is equal to m. I can rewrite that as log base e of m is equal to 6. So again, start with the base, go across the equal sign, and set it equal to the exponent. Okay, one more and we'll call it good. Let's do a to the 4th is equal to 2.4. So a to the 4th is equal to 2.4. Notice that that's in a form that you could solve. You could solve that form. Okay, but we're going to rewrite that as log base a of 2.4 is equal to 4. Okay. So you've now translated between the two different forms, and it just takes practice, and you should be able to go between the two forms fairly quickly and fairly easily, because what's going to happen moving forward is if it's in log form and I cannot do anything with it by manipulating, I'm going to take it to exponential form. If it's in exponential form and I can't manipulate it, I'm going to go back to log form. So we use them in order to undo each other because they're inverse functions. So let's do a little bit of that. So we're going to evaluate or find the exact value. And this means without your calculator. The problems with your wonderful calculators is they will do logs with different bases, which causes problems. So I want to know what log base 8 of 8 is. So log base 8 of 8. Okay, so for today, what we're going to do is we're going to set this equal to a dummy variable. So step 1, we're going to set equal to, and I'm going to use n. I don't want to use x here because I don't want you to get used to solving this way. So we're going to set that equal to n. Then we're going to come in and switch forms. So when all else fails, you take it to the other form. So we're going to switch to exponential form. So I'm going to pick up my base, that's the 8. I'm going to go across the equal sign and pick up the n, set it equal to the inside stuff, which is also an 8. So this springboards off of yesterday's, so now we're going to solve. And that's by making the bases equal. Well, we already know that there's a 1 sitting over there on the right side, so n is equal to 1. So what we're saying, so in conclusion, so log base A of A is equal to 1. So 1 is the final answer. Okay, something really momentous just happened, and this will become a property, is that log base A of A is equal to 1. So then this gives us a property that log base A of A is equal to 1. And there it is. So anytime the base and that inside are the same, you get a 1. Now, just so we can quit calling it the inside, the stuff that's inside has a name. It's called the argument of the function of the logarithm. So it's called the argument. So if I call it the argument versus the inside, that's what it is. So okay, let's do a couple more of these just to get some practice. Any comments or questions? Does it look familiar? A little bit?
Yeah.
Yes.
Okay, good. Woohoo! Okay, what if we have log base 3 of 1/9? So the argument or the inside this time is 1/9. So log base 3 of 1/9. Okay, so we're gonna do the same thing. We're gonna set it equal to a dummy variable n, and then we'll switch forms. That would be 3 to the n is equal to 1/9. So we now know that we need a base of 3 on both sides. So we're going to manipulate the right side. We know that 9 is 3 squared, but it's still in the denominator. And we saw yesterday that to bring it up, we'll change its sign on the exponent. So that would be 3 to the -2 now. Now that the bases are the same, we'll set the exponents equal. So the answer is -2. So back up top, we know that log base 3 of 1/9 equals -2. And logarithms, unfortunately, are one of those things where you need a lot of practice at it to feel comfortable, but it's always at the end of the course. So it's hard to get comfortable because you finish the course. You will see it in the regular pre-calculus class. So for those of you moving on in math, let's do log base 10 of the square root of 10. So log base 10 of the square root of 10. So we'll set it equal to n. Switching forms would give me 10 to the nth equals the square root of 10. Okay, well, we have the 10s. The question is what do I do with that square root? So if you remember from previous exponent work and probably the 101 course, that when you have the nth root of an argument, that's the same thing as x to the 1/n power. So a radical is a fractional exponent. A denominator is a negative exponent. So what that means, because there's an invisible 2 right there, that right side is 10 to the 1/2 power. And now that the bases are the same, you can set the exponents equal. So n is equal to 1/2. So any comments or questions about that? I really like these. I think they're fun. I hope you do. Of course, I know that in my 101 class at this point in time, we were on remote learning and that got a little crazy. So there are 2 logarithms that occur most frequently. They're the ones that you should be familiar with. Okay, so the first one is called the common logarithm. Common logarithm. Okay, so this is a log base 10. So it means a log with base 10. So what you're going to see is normally we would write log base 10 of x what's going to happen is they're going to drop the base and just write log x. So in other words, if you see the word log and no base, then you know it's base 10. So if there's no base, written, then the base is 10. So whenever you see the word log without a base, it's a base 10. And this is used a lot in the real world. So the pH scale in chemistry, the acid and basic scale, is a base 10 scale. The Richter scale that we measure earthquakes in is also a base 10 scale. And the other one that's most frequently used that you may not have heard of is when you measure sound intensity. When you talk about how loud a sound is, you use something called a decibel. And that decibel is a base 10 system. And that deci means 10. So that's a common logarithm. The other one's the natural logarithm. This is mainly for the biology people. Also business, but for our class biology. So the natural logarithm is a log with base e. And we saw e yesterday is 2.7183. Okay, so what does that do for us? Well, in terms of this, instead of writing log base e of x, what you're going to really see is an ln of x. And because I don't want my L to get confused with a 1 or something else, I'll always use a script or a cursive ln for x. So ln stands for natural logarithm. The French were the ones that originally did this, and you'll notice they switched the order on that natural logarithm because it was a logarithm, a natural. So, okay, so those are the two that occur a lot, and they're just kind of like the special cases so that you can recognize them when they're on the homework more than anything else. Next is finding the domain. Okay, so when we first started talking about functions, we said we had 3 types of functions that you had to worry about in terms of domains. Anything that had x in the denominator, anything that was an even root of a radical, and then there was the anything else. So now we're going to tack on to that anything else category. So this is another type of function. So we're going to finding the domain of a log function. So what if we have f of x is equal to log base 2 of x plus 3? Okay, we can do this a couple of ways. I want it to make some sense to you as to what I'm doing. So this plus 3 is definitely on the inside. And we know that when we're on the inside with transformations, that's going to shift the graph how? Left or right?
Left.
Yep. So this would shift my graph left 3 units. So we graphed that log base 2 a few minutes ago. It has an asymptote that was sitting right on top of this axis, and it had a point that was over here at 0, 1. Well, I'm going to take that point of 0, 1 and move it left. 1, 2, 3. So it's now over here at -2. I'm going to take the asymptote and also move it left. So the graph would come up and do this. And we will do a lot more transformations here in just a few seconds, but this gets us started. Well, when we look at that, we can see that it's really starting at the asymptote and going off towards infinity. So for us, what we can do to find the domain is set the inside greater than 0, not greater than or equal to, because it can't equal 0. So in other words, why can't it equal 0? Because how could you take 2, raise it to some power, and get a 0? You can't. So you're just going to take that inside, set it greater than 0, and solve it, and that'll give us our domain. So our domain, we can see, is from -3 to infinity, which matches with our picture. Well, that was pretty easy. Let's do another one just to make sure everybody's on board. What if we had g of x is equal to 2 plus log base 5 of, I'm going to do 1 minus 2x just to make it a lot uglier. You're not going to have to graph anything that looks like this. Notice this 2 out in front would shift it up, but this inside stuff is making some stuff really bizarre. You've got a negative on the x, which would be a reflection and all kinds of stuff. So instead, we're just going to follow the directions. We're going to take what's inside and set it greater than 0. Again, the 2 that is sitting out in front does not impact the domain, and the base doesn't impact the domain. So even though this is a base 5 or this was a base 2, the directions are still good. You're just going to take the argument, the inside, and set it greater than 0. So that's a negative 2x is greater than a negative 1. And now we'll divide out that negative 2. So x is less than a positive 1/2. So that's that reflection. So that negative on the x reflects it. We can see that happening. So our domain is going to go from negative infinity to 1/2 with a parenthesis. But let's get some more graphing under our belt. And that's the last of the special domains that we have. So it's kind of nice. So anytime you have a radical, you have a problem. Anytime you have x in the bottom, you have a problem. And anytime you have x in a log, you have a problem. So got restrictions. Okay. So let's come in and graph using transformations. So this is one place that the online homework and even the textbook is a little light on examples. I think they should have more than they do, but they don't. Let's do f of x is equal to log, and I'm going to use base 5 again, and let's do x minus 2. So log base 5 of x minus 2. So the first thing you have to get over more than anything else is that the base doesn't matter. That's the base on the exponent we saw yesterday. That base didn't matter. The pictures all looked the same. So again, our base graph, and that would be y equal log base a of x, is this. And the asymptote is sitting right on top of the x-axis. And that's the 0.1, 0. Somebody once pointed out to me, well, how do I get the log and the exponential correct? Well, to me, the exponent makes sense because it's increasing without bounds and it increases quickly. But what somebody pointed out to me a long time ago is that log starts off LO and the 0.10 looks like LO. So they kind of go together. I don't know if that helps or not. Okay, this 2 is on the inside. So that means we're going to go what, right? 2. So all we have to do is pick up our point that was at 1, 0, and go to the right 2. So now we're going to be over here at 3, 0. That's that anchor point. I'm going to pick up the asymptote that was on top of x equals 0 and move it also to x equal 2. And the minute I've done that, I start right next to the asymptote. I cross at my x-intercept, and then I head off without that. The book is going to ask you again, or the homework will ask you for the domain, which in this case is from 2 to infinity. You can see that a couple of ways. The picture tells me it starts at 2. If I set the inside greater than 0, it starts at 2. The range for any of the log graphs is all real numbers, so negative infinity to infinity. And the vertical asymptote is sitting over here at x equal 2. So they're pretty straightforward. They're just as easy as yesterday's, if you've done yesterday's. Since it's not due till tomorrow, you may not have. Okay, we can move it left and right. It also makes sense that we can move it up and down. So let's do one that's up or down. So let's do g of x is equal to 3 plus log base 4 of x. And again, I'm going to keep using different bases until I get you past the point where you care about what that base is, because when you're graphing or finding domains, it does not matter. So we can see that this 3 is outside because it's not written as part of the log term. So it's outside, and that means we're going to shift the graph up 3. So I'm going to take the point that's at 1, 0, and I'm going to go up 3. So now it's up here at 1, 3. It's not going to do anything to my vertical asymptote because we're moving it up and down. So it's still sitting right here on top of the axis at x equals 0. We'll start next to that vertical asymptote. We're going to head up towards our 1 point, our anchor point, 1, 3, and draw the same general shape. So could you plot more points? Yeah, but it would be pretty ugly to plot more points. We'll show you how in just a minute. So we can definitely move it up or down. Not very exciting. Can we do some reflections? You bet. So h of x is equal to log base 2 of negative x. Log base 2 of negative x. Okay, so that negative is on the inside. So we know that on the inside is affecting things in the horizontal direction and the x direction. So that's going to change the sign of the x values. So that's going to reflect this thing across the y-axis. So the point that was over there at 1, 0 is now going to be over here at negative 1, 0. You still have the asymptote at 0, so x equals 0 is still an asymptote. This time, it's going to start next to that asymptote, cross the x-axis, and head to the left. So that will change your domain. So this time the domain is going to go from negative infinity to 0. The range is still all real. So. You could also reflect this thing over the x-axis by putting a negative out in front, which makes sense to us too. So all the transformations that we've been learning work here. It's nice. It gives you some continuity to the class. So. Okay, you do have one problem that's like this. So I kind of want to walk you through one of these. Okay, so given f of x is equal to the natural log of x plus 4, the natural log of x plus 4. Part A, we want to find the domain. It's a long problem. It's got multiple parts. Okay, let's find the domain. We already know that what we're going to do is take the inside and set it greater than 0. So x would be greater than negative 4. So that would be negative 4 to infinity because it's pointing to the right. That was easy. We'd already talked about that. Part B is asking us to graph that. Okay. So graph that function. Well, luckily we know our transformations. The point would normally be at 1, 0. We're going to shift it left 4. So 1, 2, 3, 4. That's now over here at negative 3. So negative 3, 0. The asymptote that should be at 0 gets moved over also. So it's at x equal negative 4. And the graph comes through and does this. So that was easy enough. Comments or questions? Hoping it's tying together in your brain quite well. Okay, from the graph, part C says from graph, find range and asymptote. Again, it only has one asymptote. So the range of any log function is negative infinity to infinity. We can see that. Starts down here at negative infinity, goes off towards positive infinity. And it has a vertical asymptote at x equal negative 4. So part D says to find the inverse function. This we haven't done yet. Find the inverse function. Now we already know, since we're starting with a log, that the inverse function should be an exponential. We're going to follow the same steps that we did last week. So we're going to replace f of x with y, so y equals the natural log of x plus 4. Okay. The next step was to switch the x and the y to find the inverse. So we're going to say x equals the natural log of y plus 4. And now we have to solve for y. So again, I'm just following those same 4 steps from last week. To solve for y, I'm going to rewrite this to make this a little bit friendlier. So I'm going to take out that ln and write it as log base e of y plus 4 because it's easier to work with that e. Well, how do I solve for y? Well, we're stuck doing what we were doing almost at the beginning of the lecture. In order to free y up, because it's trapped inside the logarithm, we're going to switch forms. And this is why you will see the exponent coming in as a function here. So this is e to the x is equal to the inside y plus 4. And then all we have to do is move the 4. So e to the x minus 4 is equal to y, which is your inverse function. So e to the x minus 4 is equal to the inverse function, or is equal to y. So just like we predicted, since we start off with a natural log or a logarithm, the inverse is an exponential function. So, okay, and then what they want you to do is to graph it. So then graph, so part E, graph, and then find the domain and the range and so forth. So I'm just going to put its graph on top of the other graph just so we can see them as inverses again. So e to the x minus 4 is our exponential graph shifted down 4. So normally it would go through the point 1, 0. I'm going to go down 4. So I now have this point at 0, negative 3, which makes sense. The asymptote that would normally be right on top of the x-axis is now going to get shifted down. It's down here at negative 4, and the graph is going to come up and do something like this. So here's the inverse, and then the black version is the original function. So there they are. And notice, again, just like last week, that if they're going to cross, they're going to cross right along this line, y equal to x. So not only do the asymptotes cross on that line, but the graph themselves will cross. And it crosses twice. You get this kind of fishy looking shape in the middle of it. So you have one of those with lots of multiple parts to it, but only one. Okay, we're almost done. I know you're thinking, aren't we done yet? It's already at 9:33. Comments or questions about the long problem? As much as I wanted to put one, you're good? Okay. I wanted to put one on the exam, but it's just too long. Takes a while to wade through. Okay, and then we wrap up section 6.4 by solving equations. So just like we wrapped up yesterday, we're gonna do the same thing today. So we're gonna come in and solve. And do log base 3 of x is equal to 2. So I wanna solve that. The key here is you need to switch forms. So every time you start with a log, go to the exponential form and you'll find things very easy. So this would be what raised to the what. So switch forms for me. So that's log base 3 of x equals 2. So the base is
3.
And we're going to raise it to the what power?
Second.
Equals x. 3 squared is 9, and you're done. So x equals 9. Yay! You've solved your first logarithmic equation in our class. How about log base 2 of 2x plus 1, and we're going to set that equal to 3. No, let's set that equal to 4 just to be different so we don't have so many 2's and 3's. So log base 2 of the quantity 2x plus 1 equals 4. Okay, so you take a second and write it down. So this would be what raised to the what power is equal to what? It's very descriptive.
2 to the 4th equals 2x plus 1.
Beautiful. And 2 to the 4th is 16 equals 2x plus 1. So moving and solving from there, we get 15 equals 2x, and x equals 15 over 2. Okay, now you could technically check these. They're not as nice to check as you think they are. You can plug the 15 halves in. 2 times 15 halves would be 15. 15 plus 1 is 16. Log base 2 of 16 is 4, or 2 to the 4th equals 16. So they're not as nice to check, but you can check them. Okay, let's do one more and call it good. Let's do one with e. So what about the natural log of e to the negative 2x equals 8. So the natural log of e to the negative 2x is equal to 8. So it's hard to translate it when it's written as ln. So the very first thing we're going to do is rewrite it so we can see a base. So that's log base e of e to the negative 2x is equal to 8. Okay, then switch forms. So this is what raised to the what?
E to the 8 equals e to negative 2x.
Good. Yep. You're correct. So e to the 8 equals e to the negative 2x. And now that the bases are the same, we'll set those exponents equal, and x equals a negative 4. And then you're done. Again, a little awkward to check it. They'll get a little easier to check once we get the log properties under our belt tomorrow. So, okay, and that's your homework for tonight. That is due tomorrow night. So that gets you through everything that is due tomorrow. And then tomorrow what we do is come in and learn how to manipulate so that we can solve equations next week. A reminder that, again, the very last week of class, which is the last week of July, you have a test on Tuesday. You have a test on, the final exam is on Thursday, our due dates. So I'll be sending out your access codes for the final exam. You just have the access codes for the 1-hour exams, not that hour or the 140 minutes for the final exam. So I'll get those sent out either today or tomorrow. I've put the exams into ProctorU, so they should be okaying them. So we should be able to start getting things scheduled by the end of next week. So any other comments about today or what's due today or what's due tomorrow, I guess?
No.
Looking for
No.
microphones on the side. Okay, well, you guys have a wonderful day. Here in Pueblo, we're at least 10 degrees cooler. We had 104 yesterday, hottest day yet. So hopefully we're cooler today, only in the 90s. Have a good one.
Thank
you.
Bye.